Thanks. So my name's Cheryl Pottle. I'm the Regional Sales Manager for Gobain PAM, and I cover the South East, South West Wales and the Channel Island for my sins. Welcome everybody. Thank you very much for joining us today, and we hope that you get a lot from it. We are going to be recording today so that we can actually share this later. So there are some people that couldn't make it, and we will be able to put that later on social media or on a YouTube link. So we'll make sure that you get a copy of that so you can share that freely with your colleagues. Today is based, it's a seminar based on showing you the benefits of using ductile iron for directional drilling. And for that, I'll hand over to Simon Cottingham, who is going to be presenting today.
Afternoon, everybody. Simon Cottingham. I'm responsible for major projects for Saint-Gobain. So the presentation is focusing on ductile iron and directional drilling no-dig techniques. So I'll start just by going through some of the key points of ductile iron, the product range that we offer, and then get into more detail on the directional drill. So we'll crack on.
Lovely. If you'd all be kind enough to mute your microphones and turn your cameras off, we'll have a Q&A session at the end, but actually do feel free just to, if you have got a question whilst we're going through, just put your hand up and we can also respond as we go along, so we don't mind that. Okay, thank you.
Okay, a company was established manufacturing ductile iron in 1856, just a few years before myself and Sean Greenwood started in the industry. Sorry for that, Sean. We manufacture about 12,000 kilometres of pipe per annum. We supply to 140 countries. The production plants have upwards of 1 million tonnes production capacity and 45,000 tonnes of pipe fittings capacity. That's bends and tees, etc. We do have manufacturing plants in China and Brazil and South Africa, but predominantly the production is focused in Europe and primarily in eastern France and Spain for pipes. Sorry, we're not moving on very quickly. We manufacture water pipes and fittings up to 2 meters diameter, typically from 80 millimeters, 60 mil in Europe. Pressure range up to 64 bar in this range, and the minimum we'll go to is down to 25 bar. So it's high pressure, large diameter systems. The same range are available in sewerage pipe systems up to 2 meters diameter. Again, similar sort of pressure ratings available. Difference between, it's the same pipe, clean and dirty water. The difference is predominantly in the internal linings. A clean water pipe is blast furnace cement line, typically for potability and compliance with DWI reg, and sewer pipes have calcium aluminate cement water lining on them, meaning they're more suitable to a wide range of aggressive effluents. You can directional drill with both clean water and dirty water pipes. It's exactly the same pipe with the different linings that you would use for all applications, including the no-dig. Manufacturing pipes, we melt the ductile iron to about 1500 degrees centigrade. We put it in a hopper. Here at the end we have a pipe mould spinning and the molten metal is poured into the spinning mould, and the pipe is cast using a centrifugal process. So here you can see a large diameter pipe still spinning, being pulled out of the mould. So that's how we make pipes, and that's why pipes are always a set length. So often people ask us, can you make a small pipe? We can, but we have to cut it from the standard set length. So up to 600 mil pipes are 6 meters, 700 mil to 1000 mil, they are 7 meters long, and 1200 mil through to 2 meters, they are 8 meters long. So that they are all cast to a set length. Ductile iron is an extremely robust and strong material. This isn't the standard offloading procedure at our stock ground, but it does demonstrate that if you drop a ductile iron pipe, unlike a cast iron pipe or a pipe of a different material, it doesn't need to shatter into 1,000 pieces. It's the ductility, the strength is in the metal ductility and its molecular makeup. So it's an extremely strong material. Sorry, we've already played that one. extremely flexible material. So again, due to the ductility, the pipe has a great deal of strength to the extent that it will or can be bent to this level and will spring back into shape after that bending. It's a simple push fit socket spigot joint, so you can see the gasket here housed in the socket. When the pressure inside the pipe acts on the fins of the gasket, it pushes the rubber onto the spigot and the socket. So in effect, the higher the pressure in the pipe, the better the gasket seals. That's not to say it doesn't seal at low pressures, but the higher the pressure, the better the thing is sealing and the more robust the joint. You've got flexibility of joint up to 5 degrees angular deflection, which obviously comes in important when we're directionally drilling radiuses of angles of pipe. It accommodates rather than resist ground movement. So unlike welded systems where the pipe's trying to resist movement, the joint will flex and move and accept that joint movement. And a properly made socket spigot joint, so you can't put into service and test a joint that isn't properly made, i.e. has a leak path. But once that joint is properly made and tested, you have confidence of excess of 100 years plus joint integrity design life. So it's a high integrity, long serving pipe system. Talk about identifying joints at test. We now have a gasket that you can actually test in situ before you backfill. I'll show you a little bit of that in the next slide or so, but that gives an extra degree of integrity and certainty in that where previously you might have to bury backfill and cross your fingers that everybody done everything correctly. Now you can actually perform a test before you backfill. Again, we talked about joint deflection. We talked about joint deflection. This gives you some idea of the angular rotation of the socket spigot joint. So that's when we talk about accommodating ground movement. It also allows us to lay pipes at radius and sweeps. Again, something that's required when we're directly drilling or using pipes in no-dig applications. The joint is given a very rigorous test. So in terms of its positive internal pressure, we test every pipe to the pipe is tested to 1.5 working pressure plus 5 bar. So where our minimum pressure rating is a class 25 bar pipe, we will test it to 30 bar plus 5, so 35 bar test. So it gives a very rigorous internal pressure capability. In terms of negative pressure, we can go to minus 0.9 bar negative pressure. We also test cyclically, so we'll take the pressure, its working pressure plus or minus 5 bar for 24,000 cycles to replicate a pumping regime. And also, again, critical for directional drill applications, it's capable of 2 bar external pressure. So that's to say 20 meters head of water trying to force its way back into the pipe, unpressurized pipe. The joint is capable of resisting that pressure. So it's a high integrity socket spigot joint. I mentioned about testing. Just as a quick aside, we have a gasket now that allows you to test in situ. It's called Sure Joint. We're introducing it across our diameter range. The gasket, or the pipe rather, has notches in the socket face. The gasket has a nozzle that's sited in one of the notches, and that allows you to do a simple air pressure test on the groove in the gasket, which we'll see in a little while. So this groove here, so once the joint is in the gasket rebate and properly sited, this is an air pocket that can be tested to check for gasket integrity using this particular tool here. So just a quick aside, I'll not go through everything, but that's quite an interesting new addition to the range that I think will be is welcomed by people in allowing a test before backfilling. So moving on. So we have a range of mechanical anchor joints, primarily to negate the need for concrete thrust blocks at bends and changes in direction, but that can also be used to facilitate no-dig and directional drill applications. So the specific joint we're going to look at for directional drilling applications is what we call the universal VE joint. So that joint has a double chamber system. A gasket giving you the water pressure seal is housed in this chamber, and in the front chamber we have a ductile iron locking ring and a well bead on the spigot of the pipe. So when the spigot is inserted into the socket, the well bead passes the locking ring, and when it's to the other side, the locking ring grips down behind the well bead on the spigot, preventing the spigot withdrawing when it's under pressure or when it's being pulled. So that's how that is the joint that we use for these applications. Only a second. So talked about a metal locking ring. The universal joint starts with a series of ductile iron segments, which we put together offline. There's a rubber link that allows the joint to flex and stretch. There are these pins that are put in there to link the rubber together and to link the locking rings together. So this is made up in segments. Takes about 5, maybe 10 minutes, depending on the diameter, to construct a locking ring. So once that's all put together, we have the socket here. Talked about the 2 chambers. The chamber for the inside chamber that takes the gasket sits in there, normal way, nothing unusual. The outer chamber then takes the locking ring. So we clip the locking ring to evenly distribute it around the socket circumference. So a series of clips starting at the top, and we work our way around. So this operation would take you around about a minute and can be done, as I say, offline before the pipe's offered up for installation. And this just, as I say, stretches the ring to allow the spigot to be offered up to it. So once that is very slowly clipped into place, we'll see the spigot appear, and the spigot, you will notice, has a well bead around the circumference, so you might see the little lump there. So when we push the pipe spigot onto the locking ring, as soon as the locking ring's resting on the spigot, pull all the clips out, carry on with the push. The well bead goes past the locking ring. When it's under pressure and in tension, well bead can't pass the locking ring, and that locks everything together. Just to show it in real time, this is a locking ring to be fitted. So you can see the steel locking ring hanging there. 2 guys can lift it into place, about 25 kilos or so in weight, again dependent on the diameter. You see the gasket inside the chamber, and you see how quickly and easily it is to clip that into place. I think you'd agree that's probably a little bit quicker than the video suggested. And once that's in position, we can carry on with the jointing. So that's the joint that we use for directional drill applications, the universal VE joint. Now we're going to look at specifically ductile iron in directional drill applications. really, there's nothing a great deal different between directionally drilling ductile iron and directionally drilling other materials such as polyethylene and steel. The techniques are exactly the same. There are slight differences in terms of some benefits that we think ductile iron has in certain applications, but it's pretty much the same process that you would do for any material. So we drill a pilot hole. Again, nothing unusual there, other than the radius that we have to adhere to. So obviously the socket spigot joint has angular deflection, the socket spigot anchor joint, and you see there angular deflection of 3 degrees up to 500 millimeters that can give you a minimum radius curve of 115 meters, 600 and 700, 2 degrees deflection, sorry, an 800, 2 degrees deflection. So you've got a 172 meters radius, and that drops off as you get less angular deflection. The radiuses increase at the larger diameters. So obviously you have to ensure the pilot hole and the drill are within those minimum radiuses. We then enlarge the pilot hole. Again, nothing unusual. There are suggestions or guidance in terms of the size of that hole relative to the outside diameter of the socket. When we say the outside diameter of the socket, the outside diameter of the socket rather than the outside diameter of the pipe itself. So for drills less than 50 meters, we recommend 1.2 times the socket diameter, 50 to 100 meters, 1.3 times, 100 to 300, 1.4, more than 300 meters. And if it's drilling through rocky ground, we recommend 1.5 times the outside diameter of the socket would be the pilot hole size. Sorry, the drill size. And then we pull the pipe in. So this is where we have a couple of options in terms of pulling. We can either pull in a full string of pipe, and this one I think was 600 millimeters diameter from memory. So they put the entire string together before commencing pulling the pipes in. One way to do it. Because the pipes are short socket, relatively short at 6 meters long, and the joint is relatively quick to put together, there is an option, as they're doing on this application, where they had limited space behind the drill, to actually put the pipes together as the pipe is being pulled into position. So you can see they built this launch ramp here. They're actually jointing the pipe as it's moving along, which is another technique that you can potentially consider, and one of the benefits potentially of iron socket spigot versus welded systems, where the time taken to, for example, weld a polyethylene pipe together will be such that you wouldn't really be able to butt fuse in short lengths as the drill's taking place. You really would have to weld the whole section together before you made a start. Sorry. So you also have to consider lubrication of the hole, which is normally done with bentonite slurry, flooding the hole, which allows the pipe to be pulled through easier with less friction and reduce pulling forces. Above 300 millimeter diameter, because of the buoyancy of an empty pipe, to center it in the hole, you do need to ballast that pipe, which is achieved by putting another pipe, a temporary pipe, inside the drill pipe, and potentially filling it with water, dependent on whether what level of ballasting is deemed to be required for the length of pull and type of pull. So this is all to allow the pipe to be pulled through with minimum ease, obviously. And there's a bespoke pulling head to also do to facilitate that operation. So that's pulling the pipe and ballasting the pipe. We already talked about angular deflection of the joint and the minimum radiuses that can be achieved with that deflection. We've also got recommendation on maximum pulling forces. Now this is linked to the capability of the universal VE anchored joint itself. So we have maximum pulling forces that or allowable pulling forces that you need to stay within that can be, obviously to facilitate the pull, and that's all about the ballasting and easing of the friction of pulling the pipe through the hole. So full guidance on that and full assistance from the technical support team to work out bespoke and specific for your job what's required in terms of all that, including ballasting. In terms of the external protection system, because you're pulling the pipe through a hole that could be abrasive with elements in that could damage the pipe, we have a robust external protection system. There are 3 options. So up to 700 millimeters diameter, it's an extruded polyethylene coating on the outside of the pipe. So very robust polyethylene shell, which protects from damage. At 800 mil to 1000 millimeters, it's a sprayed polyurethane coating of a similar robustness as the polyethylene coating, but for the larger diameters. And if you are pulling the pipe through extremely rocky or difficult ground, there is also a fibre cement external coating jacket for particularly robust applications. So again, a series of external coatings relative to the application, and again we can give guidance on which one's best suited to your application. There's full technical backup service for the project to consider all the parameters that need considering, and that's available. If you want to discuss a specific set of requirements, we can assist with that. As well as the directional drill, also in the no-dig sort of stable of offers is pulling pipes through casings or tunnels. So we're doing a lot of this now in the UK, pulling pipes in pipe sleeves on the motorways, rivers, road, rail. So and ductile iron really is becoming the material of choice for that because of its relatively short length relative to the shaft size, the fact you can drop the pipe down the shaft and pull it through and keep making the joint as you're pulling through. There are real benefits to the ductile pipe in that no-dig application. This is one example we did up in the northwest, up in Keswick, which was a 280 metre pull of pipes in a tunnel under the River Greta. You can see it was in this case, a twin pipeline. So we had bespoke carriages here that we sat the pipes on that had runners and wheels on the underside so that they were dropped down the shaft. The joint was made at the neck of the tunnel on these spiders, and then the pipe was pulled along till it rested here again, and then the next pipes were dropped down and the joint made. So that was a very successful project. As I said, the shaft here was probably about 9 or 10 meters in diameter, so not a lot of space, but just enough to lower the pipes into position. A couple of flange sockets and blank ends, and pulled everything through. The blocks here, interestingly, weren't anything to do with guiding the pipe through. This was because they weren't going to grout the tunnel up afterwards. They were going to leave the carriages in position, and these are zinc blocks to galvanically cathodically protect the steel carriages from corrosion, so that they didn't cause the pipe to drop in the tunnel. So that was an interesting one. In this application, again, the flexibility of the joint is a real benefit because there are tunnels with radius and curve, and that can cope with it, but there are also uneven tunnels. So we sometimes see in these applications double flange pipes proposed to pull through, which is not a great idea, because if there's any unevenness of tunnel and flange pipes have to span unsupported, which they can do, you are going to stress the flanges and bolts. Not to mention flange joints don't have a indefinite lifespan, whereas the socket spigot joint gives you 100-year plus design lifespan. So if you see anybody proposing to put flange pipes in tunnels, I would strongly recommend against it and recommend using the socket spigot universal VE joint for that application. Another example was an 1800 mm pipe where wasn't planned this one. They were laying the pipe along and then realised they were going to have to dig a trench across the main access to the works and leave it inaccessible for a few weeks, which wasn't deemed to be a good idea. So this was a hastily dug tunnel of minimum dimension. This is an 1800 mm pipe that really was scraping the sides as it was pulled through on a couple of skis at the front here. Not too long a pull, but quite tight. And as I say, successfully pulled through on a ski. And this is a job in Italy, 1000 mm pipe, again pulled through an existing culvert. Again, this ski design was quite useful because the culvert had a lot of unevenness and gaps, and the ski with the curved up end was ideal for pulling across the uneven surface where spiders or wheels might have snagged as it was pulled through. So again, directional drill, one method that we use in no dig, but certainly pipes through tunnels and casings is certainly becoming something that we're doing on a fairly regular basis now. Not a lot of this done in the UK, but apparently quite a lot done in Europe is ductile iron pipe bursting. Obviously a lot of pipe bursting done with other materials in the UK, but they do pipe burst using ductile iron. And when you think about it, it's quite an ideal material because you're pulling it through an existing pipe. When you burst the pipe, there's going to be shards and materials burst into the ground that, if it's a polyethylene pipe following up behind, potentially gets scored and damaged, which isn't good for polyethylene, compromises its lifespan, whereas a ductile pipe can take that degree of scraping and scratching. The protection systems of ductile iron can re-heal themselves. They're designed to scab over scraps and marks on them, as well as protecting the general pipe. So in terms of pipe bursting, and ductile iron, certainly in Europe, is seen as a real benefit and an advantageous material. Again, it's the same technique as you would pipe burst with other materials. It's obviously not as bendy as other materials, so you have to drop it into shafts to pull it along. But as I say, it has its pluses in terms of that application. So just some reference schemes, some examples of where directional drill has been done, has been used over the last 20 years. A lot of projects in Europe. I'll show you some of the examples, but many projects in Europe and a few in the UK, but not as many as we'd like, for whatever reason. I think directional drilling is inherently a risky business, and I guess one of the issues is people tend to stick with what they know, so moving on to new things is maybe not encouraged in this country, whereas in other countries they embrace it. I don't know, but a lot of experience, a lot of pipes installed directional drill in Europe. This project's an 800mm diameter project, 280 meters. As you can see, they made the joint prior to pulling it in this instance. Flooded the trench and pulled the pipe through. You can see the projects here, the number of directional drill pipes in various diameters. Clearly many more projects in the smaller diameters, but starting to move up the diameter scale. Here's the project at 800mm, a few projects at 700mm, and you can see the length of those pulls, or the average length of those pulls. So you see 400mm, averaging at 600-700 meters per pull. So they're not insubstantial projects, and not insubstantial in terms of numbers. So you can see there 90 kilometers of pipe has been installed using directional drilling techniques. And I'll play this, which is a greatest hits of the various projects that have been undertaken. So some examples. This was a project spanning some estuaries in Europe. I'll move it along a bit quicker. So yeah, 350 meters, 300 millimeters. The drill was on the island in the middle of the estuary, so they couldn't string out long lengths of pipe. So they set up this rig with the directional drill pulling head, and were loading the pipes as it was as the drill was progressing. So we've got the pilot hole there, and you can see the pipes moving along. That's your directional drill. That's the locking ring fitting in the chamber. Different locking rings for different diameters. At the smaller diameters, it's a single split ring. At the bigger diameters, it's a sectional ring that I showed you. But you can probably make out the pipes moving along slowly, and they're just loading the pipes onto that launch shaft. And as you say, very simple, easy push fit joint. Very quick and simple. This sheath just put over to stop any bentonite or slurry getting inside the joint. The cone just keeps the sheath in place. But you see there, nothing unusual about the technique or the equipment being used to directional drill. And there you see the pipe out the other side. So this was the other side of the shaft, and you can definitely see the pipe moving along as they're making the joint there. And this is a larger diameter, a 600 millimeter project. That's the directional drill pulling head. Your pipes with the, you see the white colour, that's your fibre cement external jacket on the pipe, external coating. Again, nothing unusual about the process of pilot hole reaming out to a sufficient size. Somebody died on site there, they're carrying him away. So you've got the reaming out the hole to sufficient size for the pipe, plus the times 1.5 probably at this diameter and length. And here you can see they're going to make the string of pipes up before they put the pull in. So this again is one of the split ring locking rings. The pipe there is the ballasting pipe that they're sliding it over. So you see the pipe with the well bead around the circumference. This just spaces the locking ring at this diameter. This just holding the ring apart. See the spigot's offered up, well bead around the circumference. As soon as that spigot is resting on the locking ring, they'll pull the clip out, carry on the pull. There we go. So that process repeated down the line. You'll have to forgive the health and safety lack of gloves. Life is cheap in Europe, I think. So you see the locking ring there, sheath across, and I'll just knock the cone down. That keeps that in place. So once all that is done, we've got the string together. Fill the trench up with the bentonite slurry. This demonstrates the flexibility of the joint as they're lowering it in. Again, forgive the man jumping in the trench in a short while underneath the pipe as it's dropping in, but missed him off. But we can see the sort of deflection you get on the joint, all locked together. So once that pipe's in place, sorry, I've gone a bit too far. You've got the pulling head on the pipe. And we start the pull through. Goes in, I think, about a metre a minute, I think it was going in at. We're at the reception end now. You see the pipe coming through, and we're assured the rest of the string of pipes followed it. So that's a demonstration of a relatively short diameter, small diameter 300mm pipe done in modules, so short lengths pulled through, and an example of a larger diameter pipe where they put the entire string together and pulled it through. So two sort of examples of the difference of directional drill application. That was hopefully an informative spin through of ductile iron and directional drilling. That's the end of the presentation. So happy to hand over if anybody has any questions about the presentation or about ductile iron in general that you want to post,
So
either now or afterwards.
Got questions from Liam. So I've answered question 1 about the shore joints being available as an anchor gasket. Locking rings, why are the locking rings assembled on site rather than pre-assembled in the factory? I think it could be fair to say that we could assemble them in the factory. However, they are easier to transport in their sections and they really don't take long to assemble. Therefore, we don't offer that. And then one for you, Simon, is then how do they pressure test when installing in short lengths?
I don't follow. What do you mean? What's the difference with short lens?
So in the example that you had where they were directional drilling, but there was limited space on site, so it was putting the segments together, as in the pipe lengths, almost as they go in. Just wondering how you pressure tested that, if it was done joint by joint or.
Yeah, it is done typically at the end of the drill. So currently, I showed you the shore joint gasket. That is in the process of being rolled out across the diameter range and across the joint types. Currently, it's just available in the standard joint type, so it isn't available as yet in the universal joint that we use for directional drilling. Or with the anchor gasket. So it will be, but currently just standard joints. So you would have to do a traditional test on the pipeline, and in terms of directional drill, that will be pull it in and test at the end of the drill.
Okay, brilliant. Thank you. Thanks for that, and thank you for taking us through those slides. I really enjoyed it. Cheers.
I mean, of course, when you've put a string together on the surface, you know, that will be different. You could certainly test the string before you pulled it in on the surface. You could put an air pressure test on that, blank either end off, air pressure test to make sure you're confident of the integrity of the gaskets, and then do the pull. But you would always finish with a full, obviously, pressure test, hydrostatic pressure test.
Yeah, and is that so after you pull it through, even after stringing it up, you air test it, pull it through, and then you'll pressure test it just to make sure nothing's changed.
Yeah. I mean, you wouldn't want to do a full test mean, I guess you could potentially, but you wouldn't want to do a full test above the surface with the string of pipe. But you could certainly do an air pressure test, which would give you a very good guide as to if there was any potential problem before you pulled it in. But again, you know, the instances of leaking joints due to failed are really Chinese whispers. Suggest there are more than they actually are. If there were as many as people suggested, all we would ever do is go out to pipelines that are leaking to check them, and we really don't. I think, you know, as long as you follow the proper procedures of cleanliness of joint, proper rebating of spigots, of inserting straight rather than an angle, as long as you follow those really basic techniques, you know, you should 99.9% of the time get good leak-free joints.
Okay, thank you.
Cheers.
It might be worth, Simon, it might just be worth, oh, sorry, I'll let you go first, Sean.
Got one for Sean?
Yeah, just I appreciate it. I mean, Simon mentioned at the beginning, me and him have been around that long. This was new technology when we started about 20 years ago. This is a new technology now. How long have you been doing this for directional drilling on ductile iron?
I mean, directional drilling, I think I did the first one in the UK probably mid-1990s, but they've been doing it in Europe well before then.
And I think that's linked to the video. I mean, you did mention it. Certainly what we used to do in the old days in terms of health and safety isn't acceptable now when you're showing some of the old videos there.
Yeah.
The technical question I've got is, you mentioned the maximum torque on the universal VE joint. How often does that become a problem, and is it over a certain size and weight of pipe that it starts to, you know, be an issue?
Well, I mean, there's a maximum force that can be exerted on the pipe. I mean, they typically determine it by the maximum operating pressure of the pipeline acting on a blank end would be the maximum thrust force. So that tends to guide the maximum pulling forces that we recommend are applied to the pipe. But they're pretty high, and as I said, the idea is to ensure that you get nowhere near those pulling forces exerted by the ballasting and by the bentonite lubrication.
Yeah, no problem. It's just I didn't know if it had become a limiting factor on length or diameter, but by the sound of it, not at the moment.
Yeah, I mean, I think we looked at a project up in the northwest, which was the 1200 mil one that was linked to Keswick. I think it was 1.2 kilometers of 900 millimeters from memory, and I think we were happy that the joint could be pulled. Not a directional drill, that was through a tunnel, but you know, 1.2 kilometers of 900 pulled through a hose pipe was certainly possible. So, you know, you get some pretty long lengths at pretty big diameters that fall within its capability.
Thanks, guys. Appreciate it.
So I guess I think this would probably be a good point, Simon, to actually just highlight those key benefits for the ductile iron material for use for directional drilling against other materials.
Yeah, I mean, in terms of its benefits, obviously its pressure capability is much better than most materials that would be used for similar applications. So, you know, we've got a minimum pressure rating of 25 bar, and that will be the standard pipe. And the big diameters, the smaller diameters are capable of even higher pressures. It's a very robust material, so you might argue that the directional drill application in itself, you're dragging a pipe through a hole in the ground. You've absolutely no idea what it's going to encounter as it's being dragged through the ground and what it's going to scrape and scratch on. So the ductile iron pipe with its external coatings is extremely robust when compared to other materials that maybe their design life is compromised by being indented and scraped and scratched. You got the length of the pipe lends itself to making the joint as you're doing the pull, rather than necessarily having to string everything together prior to pulling in. So you've got a different option on installation technique, And you know, the capability to deal with things like contaminated ground and aggressive ground. So you know, you haven't got an issue with, for example, permeation through the pipe wall from chemical contaminants that you might have to contend with other materials. So I think they're probably the key areas where you might say, and diameter as well. Of course, we've got large diameters right up to 1,000 millimeters. So they're probably the key areas where you might say ductile iron is considered as having advantages. I'm certainly not saying all the other materials are terrible. Don't use them. Use ductile iron. What we are saying is ductile iron is an option and an alternative for you to consider that you maybe haven't before. And in certain applications, it has some real benefits.
So the diameter range is DN 100 to 1,000 that's available. So just in case you want to know that. Any more questions?
Explained everything with such clarity. Then, we've got a question, Jude.
Question from Jude.
Hi guys, thank you. So I guess in your conversations with drilling contractors, what sort of response take up do you get from them? Are they geared up to undertake drills with DI? Are they familiar with it? Because that could be a potential obstacle if finding the right supply chain.
Yeah, I think you're right. I sometimes get frustrated that the contracts and the risk that we put onto the subcontractors, maybe in this country, dissuades people from trying new things. And that's not just talking about, I mean, when I say new things in inverted commas, we've been directionally drilling in ductile iron for about 30 to 35 years, but it dissuades people from taking a risk on something that they haven't done previously. And that's probably the biggest, one of the major conversations we have with the contractors. You know, we've always done polyethylene, and therefore we're always going to do polyethylene. Well, you know, that's not really the right spirit in terms of innovation and doing new things. But I think when the right scheme deems ductile iron is the best solution, then the contractors have used it, and all reports back were, it's worked absolutely fine. There's not really much difference between drilling this in and drilling other materials in, and what we were worried about.
Do you know if those schemes were more on the clean water supply side rather than a waste project?
No, I think it's been a mix. I mean, it's more often than not has been clean. A lot of our sewerage pipeline work tends to be in treatment works, to be honest, and linking processes more than cross-country sewerage rising mains. So that would probably mean more cross-country pipelines where this application would be relevant have been clean water.
Yeah, I think the main advantages you spoke about, pressure and permeation, leading to contamination. So those would lend themselves to supply projects more than waste, I think.
Yeah, absolutely. But equally, you know, if you've got to go under a road or rail with a sewerage pipe, it's you know, you can do it with this one.
Yeah, with very limited working area, like you say, you could join the pipe as you go through it.
I think that's one of the big advantages is you have an option to not have to weld up an entire string before you pull it in.
Yeah.
If you haven't got the space, then you are looking for ways of doing that.
Thank you very much.
Cheers. Thank you.
Any more questions? Did you want to just wrap it up, Alistair?
Yeah, just want to say thank you guys, really. Really informative, and I certainly learnt a lot. So thank you very much for taking the time to do the presentation.
You're welcome.
Yeah, thank you everybody for attending. So it's our pleasure. You know, we offer many different CPD seminars. Happy to deliver them over lunch and learns, or sit and do it at lunch and learn, you know, in person with your teams. So please feel free to reach out and ask for those. We're really happy to share that with you. Thank you, Simon, as well.
Yeah, no problem. Thanks for listening, everybody. Hope it was informative. If anybody thinks of any questions afterwards that you're burning to ask us, then just fire them through on the chat, and we'll endeavour to get back to you.
Thanks, guys. Catch you soon. Bye-bye.
Yeah, thanks ever so much.
Thank you.
Cheers, guys.
Bye.